Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Now then, let's get on to the first of our questions that are coming tonight. Dave in Great Yarmouth sent an email in. He says, what effect would there be on the planet if the moon was not there? Good question. Thanks, Dave. Chris?
Well, we're very lucky to have the moon, actually, because if you look at the size of the moon relative to the Earth, it's disproportionately big. And that's because it was formed in a rather unusual way, because most moons that planets and other objects have, they're objects which the big planet itself has captured as they went past, and the planets have grabbed their moon because of their gravity. Well, the Earth's moon's origin is slightly different, and our moon is actually the product of a huge cosmic pile-up. About 4.5 billion years ago, when the solar system was in its infancy, the sun was just getting constructed, and the planets were just combining themselves into balls of dust and muck and stuff. All of a sudden, we found, luckily no one was there to see it because they wouldn't be there for long, that there was a planet roughly the size of Mars, and it was on the same orbit as the Earth. And these two planets collided. Theia, this notional Mars-sized planet, slammed into the Earth, and this enormous collision unleashed an enormous amount of energy, and that ejected into space a lot of material from the crust of the Earth, which formed a big shroud or an envelope around a new ball of material, which was the product of what was left over from this collision between these two bodies. And this dust slowly coalesced, initially into a ring and then into the Earth's moon. And that explains why the moon is as big as it is. And because a lot of that dust was turning and spinning, the moon continues to this day to be turning. It's completing about one complete turn on its own axis every about one lap around the Earth, which is why we always see the same face of the moon. But the fact is the moon is exerting a big gravitational influence on the Earth and the Earth on the moon. One hangs on to the other, and thanks to the moon we have tides. The moon stabilises the planet Earth in its own inclination and its own spinning around its own axis, and therefore the Earth is a much more stable environment than it would be if the moon wasn't there. And some people have therefore suggested that the moon, because of this stabilising influence, has helped to provide the beautiful, nourishing, perfect place for life to get started and then be sustained. And even more cunning, some people have suggested that the moon may have directly helped early life to get going by creating tides, because by making salt water rush in and out, up and down beaches and things, what it was potentially doing was creating the right sorts of environments for things like nucleic acids, the precursors of DNA and RNA, to start copying themselves, because it was doing, some people have suggested, a sort of early version of the polymerase chain reaction on some early beach. So we have a lot to thank the moon for, but above all, of course, it gives us a nice white thing to look at in the sky.
Mark in Dunstable. Hello, Mark.
Hello, Sue.
Hello there, you're through to Dr. Chris. What's your question?
I watched a programme on bomb disposal guys in the Second World War, a very brave bunch of men. The Germans' fuses were packed in a thing called picric crystals, and I wondered if that's the same thing that they put on safety matches.
This is actually a chemical called trinitrophenol, TNP, and it's a bit similar to TNT, trinitrotoluene. Fuses, on the other hand, are probably a slightly different chemistry from safety matches. Matches were actually born a few hundred years ago, and it was the discovery of phosphorus that made matches happen in the first place. White phosphorus in this case, because phosphorus, if you remember, is the stuff that bursts into flame spontaneously if you have pure white phosphorus and then expose it to air. That's right. The way a safety match works is that the old style matches, when they first made matches, had phosphorus and then some other chemicals that it could burn in the match head. So the phosphorus acted both as a fuel and as the thing that got the fire going when you just gave it a bit of heat. They were obviously very dangerous because it was very easy to detonate that reaction, and they would then start a fire. So chemists slowly realised over a number of years and innovations that if you separated some of the chemicals from the match head and put them on the side of the match box, then you had, when only you put them together, the combination that was needed to kickstart the chemical reaction that makes a match burn. That's right. So what happens in a match head that's a safety match head is that they've done away with the white phosphorus and substituted a slightly less reactive form of phosphorus called red phosphorus. And white phosphorus is in the shape of a tetrahedron, so there are 4 atoms of phosphorus glued together in a tetrahedral shape. With red phosphorus, one of the bonds between those 4 bits of the tetrahedron is broken, and instead it's linked to another tetrahedron. So red phosphorus is a long chain, and this is slightly less reactive and slightly less unstable than white phosphorus. You put that on the side of the matchbox with some rough stuff, usually glass or sand particles, and then in the match head you put an oxidizing agent, so usually potassium perchlorate you put in there, because that gives away lots of oxygen when it breaks down. You also put some sulfur in there, because sulfur burns nicely, and this way, when you strike the match, the heat generated by the glass particles in the match head and on the side of the match box creates a bit of heat through friction, that's right. This turns some of the red phosphorus into a little bit of white phosphorus, which kickstarts the reaction and starts the perchlorate, oxidising the sulfur. The sulfur then burns, produces some heat. This lights the wood in the match, and then you're away. So matches are an amazing industry, but they weren't always as safe as they are now. And if you still want an unsafe match, then the red matches, the ones that you can strike on anything, all that happens there is that all the chemicals, instead of the phosphorus being on the side of the box, is in the match head, so you can strike them against anything.
All right, Mark?
Yeah, bye-bye.
Bye-bye, bye-bye. Thank you very much. That's Mark there. Now then, Dr. Chris, Hedra has a question. She says that what causes hiccups and what are they? Good question, because they always catch you unawares, don't they? Chris?
They're almost impossible to get rid of. Well, hiccups are a spasm of the diaphragm. Diaphragm is a very big muscle, which is a dome shape, and it separates your chest cavity from your abdominal cavity, and it's under the control of your phrenic nerve, which comes out of the very high level of the spinal cord, right up in your neck, and it goes down to the diaphragm, and when the phrenic nerve has some activity in it, the diaphragm contracts, and it pulls the muscle down into a more compact shape, increasing the volume of the chest cavity, lowering the pressure, and it makes you breathe in, because the pressure inside you becomes lower than the pressure outside you, so the atmospheric pressure pushes air into your lungs. So it seems paradoxical, but breathing in is actually almost a passive process, in the sense that you're actually letting the atmosphere do the inflation work. You've just had to make the space inside you a bit bigger. Now, when you get hiccups, what's actually happening is that the control of breathing, which goes on in a part of the nervous system called the brain stem, which connects your spinal cord to the top of your main part of your brain, that part of the brain has a cluster of nerve cells in it which are connected into what's called a pattern generator. And so they integrate how much you need to breathe with how much you've already breathed in, with how stretched the lungs are, and all these other factors, and they create this respiratory drive. And for some reason, when we get excited, when we get some kind of other unexpected phenomenon, sometimes brain tumours, sometimes other kinds of chemical disturbances and anaesthetic agents and things, sometimes this can trigger off abnormal activity in this cluster of nerve cells, this pattern generator, and instead of a smooth inspiration, breathing in and then breathing out, little surges of activity go down the phrenic nerve, and they make the diaphragm spasm and jerk a bit, and that's a hiccup.
Ooh. I was going to say, what about that tenner I lent you? That'll get rid of them. Mike in Colchester has asked a question about the moon, because we were talking about the moon a little while ago. Does it have a stabilising effect? Is it a bit like a gyroscope?
Yes, I mentioned to the answer to the question at the beginning, what would happen if the moon wasn't there? Well, we don't think the Earth will be half as propitious as an environment for life as it is. And I said that the moon has a stabilising effect. Scientists have looked at this, and the moon certainly does, they think, tend to contribute to the fact that the Earth is a nice environment. And one of the reasons it does that is because the Earth is spinning, and it's also precessing. Now, if you've ever had a spinning top, which is where you kind of wind it up so it's going very, very fast, it spins round and round and round, and as it slows down, it can begin to wobble. And the Earth has a bit of a wobble, and this wobble means that the tilt of the Earth can change a little bit, the attitude of the Earth can change a little bit, and this can affect the amount of solar inflorescence, the amount of energy coming in from the sun, hitting certain bits of the Earth for certain periods of time. These kinds of things can have impacts on climate. They can change the conditions on the Earth, and they mean that the Earth has a less stable environment for life. Now, the moon, on the other hand, by being in orbit and exerting a gravitational influence on the Earth has a steadying effect, and it therefore tends to help to damp or minimise the amount the Earth would otherwise wander on this precession, this wobble as it goes around the Sun. And for that reason, we think the Moon has helped to maintain this very nice, fairly well regulated, fairly calm, cyclical but over a very long time change condition on Earth, which has made it much more ideal for life.
All interesting stuff. Let's go now to John in Peterborough, who asks, if the Chilean earthquake had happened on land rather than in the sea, how bad would the destruction have been in comparison?
Oh, it was a huge earthquake. It was about magnitude 8 something. So the effect would have been absolutely enormous. I dread to think how bad it would have been. The interesting thing about that earthquake is that Charles Darwin saw the same thing a couple of hundred years ago when Darwin was actually on his journey and heading round to make all the observations that led to him eventually writing The Origin of Species. He was actually down in Chile, and the event also happened when he was there, and he wrote about it, which is just amazing to see history repeating itself. But as to whether anyone would survive if that was a land-based thing, it comes down to the same old formula, which is that earthquakes don't actually kill people, buildings do. And the thing that unfortunately made the death toll in Haiti so high was that the buildings were not earthquake-proofed. And if the same earthquake of the same magnitude had happened in a more developed country, which does experience earthquakes quite regularly, many of the buildings there have building codes now, which mean that they would have not impacted or collapsed the way that the buildings did in Haiti. The same will be true in other parts of the world. If you've got an earthquake happening and poor buildings, the buildings can fall down and kill the people. If you have an earthquake somewhere, the buildings are well constructed, or there aren't any buildings and there aren't any people, no one knows. So it all comes down to basically how well the buildings are built and how many people there are there.
More questions coming through. Let's go to the text this time. Ian, near Wyndham, asked Chris, why doesn't frost occur on an object under cover, even though the temperature is still well below zero underneath this cover? That's from Ian, near Wyndham. Chris?
Yes, hello Ian. There are a number of reasons for this, but the most obvious reason is that although the temperature may be low, there may not be enough water available to condense onto that object and then freeze. So if you look at what's happening on the ground surface when you have a ground frost, the ground may actually be colder, paradoxically, than the air. The air doesn't necessarily have to register a freezing temperature for the ground to have frost on it. So the reason first and foremost that you get a frost is that the ground is seeing a cold, dark sky because the atmosphere is relatively transparent to infrared, long-range infrared, which is heat. So when it's night time and there's a cold, dark, clear sky out there, any heat in the ground is radiated away quite quickly. The atmosphere is a poor conductor of heat, so that doesn't sacrifice or surrender its heat very quickly, so the atmosphere can stay relatively warm. The ground, on the other hand, can get very, very cold. And then where you get an interface between the air, which has got some water vapour in it, and this very, very cold surface, water vapour can settle or come into contact with the very cold surface, and it freezes and forms some ice. If you put a cover over an object, though, as there is no interface between that very cold air that's got some water vapour in it and the even colder surface, then it's much harder for frost to form. The other point is that if you've put a cover over things, then you prevent air movements, and you may also interrupt that radiation of the long-range infrared up into the sky, and so the object can have its temperature kept a little bit higher. And if you're thinking about your plants in the garden, for example, when you cover those over or put things in a cold frame, then what you're actually doing is preventing frost crystals forming on the tissues or in the tissues of the plant. And often what this will do is to directly rupture or damage cells in the plant, and that causes injury to the tissues, and then the contents of the cells spill out, and the plants get infections, and they also get their tissue damaged beyond repair. Whereas if you prevent those ice crystals from forming, then the tissues of the plant stay in much better conditions.
Next to the email, John in Cambridge asked this question, Chris. When he was at school, he says, I learned that there was a law called the indestructibility of matter, or the conservation of mass. Although it's possible to imagine that there is such a thing as infinite size, it's harder to imagine something getting infinitely smaller. Does the law mean that things can get infinitely smaller? Is there a point reached where something would go out of existence because it was too small to exist? Phew. Chris?
It's getting quite philosophical here. If you wind the clock back about 2,000 years or so to the Greek philosopher Democritus, he actually thought about this quite a bit, and he came up with the idea, in fact, he's one of the first people to suggest the concept of an atom, because he felt that you would eventually get to the point, if you kept cutting things and making smaller and smaller cuts of smaller and smaller objects, eventually you'd get to something which you couldn't cut any further. He thought that was the atom. His idea about the atom persisted for a long time, but it was then when scientists came along with particle-smashing machines, like the Large Hadron Collider, they were able to show that even atoms could be broken down into smaller components, and you have these subatomic particles. There's a whole family of those which together make atoms. But we don't think you can probably go much smaller than that. So in answer to this question, if you keep cutting things smaller and smaller and smaller until you get to atoms, you can then bust open the atoms, and the bits that the atoms are made of, we think they're probably about as small as you can go.
Cool. Bob has called in and asked, when planes land and the wheels touch the ground, we see some smoke come off them due to, he assumes, the wear on the wheels. He wondered, would that wear be drastically reduced if the wheel was already spinning when it made contact with the ground? Good question.
Well, the reason is the wheel is being accelerated from being relatively slow moving. It might be turning slightly because of the air rushing past it, depending on which part of the wheel is exposed to the airstream going past. But as soon as it hits the ground, of course, you've got the whole weight of a couple of 100 tons or more of aeroplane on that wheel, and the wheel is being accelerated to the travelling speed of the aeroplane, probably a couple of 150 miles an hour when a big plane comes into land. So you're accelerating that wheel from next to nothing to a very high speed by dragging it across the surface of the runway. And the smoke is the wheels getting spun up to that high speed from nothing. And it's a bit like you if you got in your car and pulled away from 0 to 150 miles an hour in your driveway. Apart from potentially being quite dangerous, the thing that you would have to do is to put all the energy from the car into the surface of the road to get the car up to that speed. Well, what the plane wheels are doing is the reverse. They're getting dragged up to that speed by the passage of the plane by touching the wheels against the ground. The other thing the pilot's then doing, as soon as the plane's down, is putting the brakes on, but hopefully he won't lock the wheels up. So it's more that the wheels are getting spun up to a very high speed very, very quickly, and that's why they make that bit of smoke. I don't think there'd be much merit in spinning the wheels up to a certain speed ahead of this, because the benefit of doing that would be less wear and tear on your wheels. The cost of doing that would be having to have machinery and systems in place to make that happen, and that would add to the fuel consumption and the complexity. It's another thing to go wrong. So it's probably better to have it simple, functional, and just take into account a bit of wear and tear.
Now, let's go to the text again this time. Dr. Chris, do you believe NASA will put an astronaut on the small asteroid that will pass us in 2029 at a distance of 22,000 miles? And what will they find on this asteroid? That's come in from Mike.
Well, this asteroid, yes, there is an object, a near-Earth object, which is going to pass quite close to the Earth in about 20 years' time. I don't think that anyone will put a person on it, because these things are travelling along at 20,000 miles an hour or faster. So you probably wouldn't want to put someone on there, because they'd vanish off quite quickly. And why would you want to do that? Much easier to take the low-risk option and send a probe to interact with the body. And we're doing that now. People have got various missions out there. The Rosetta mission is going to do this. There was Hayabusa, the Japanese mission, that went to interact with comets and things and try and land on these things. So we know this is possible, and people are doing this kind of thing with machines which are much more expendable than people are. The idea, of course, is to go and sample them, get bits of them and bring them home. I don't think they'll do it with an astronaut, but it would certainly be useful to do it with a probe, because these bodies that are orbiting often contain, locked away inside themselves, material which dates from the birth of the solar system. And so we get a snapshot of what the material was that spawned the planets and the material which is in our solar system. So they're like a time capsule. So it would be quite an interesting thing to do, but I can't see NASA doing that, to be honest.
Right, let's go to our email again. This one has come in from Kirsty. Hi, Kirsty. And she says, why do my nails grow quicker when I'm on holiday? Chris?
It's a very good question, that one. I think there's probably a couple of reasons. One of them is that when you go on holiday, you tend to relax more and you tend to eat better, and certainly eat more. And that means that if you eat a lot of protein in your diet, because nails are made of keratin, if you increase the amount of protein in your diet, you will increase the amount of raw material for making more of this keratin in nails, and therefore because there's more raw material, your nails could grow faster. Another thing to bear in mind is that many people do jobs which are a bit manual, or they involve doing things with your hands, and that involves wearing down your fingernails, especially if you're doing a lot of typing. If you look at the keyboard on a computer, the keys all go shiny after a while and the letters wear off. That's because your fingertips, and especially your nails, impact on the keyboard, and this has a frictional or wearing effect on your nails. So doing your job, whatever it is, often does wear down fingernails. When you go on holiday, of course, you don't do that job anymore for a while, and that wear and tear stops, and so the nails appear to grow faster, but all that's happening is they're growing maybe a tiny bit faster because of the increased eating, but they're not wearing down, so they appear to actually get bigger faster.
We've got Robin from Milton who's on the telephone. Let's see what his question is. Hello, Robin.
Hello.
Hello, you're through to Dr. Chris.
I'd like to ask Dr. Chris, what is the difference between AC and DC?
Well, let's look at DC first, because that's probably easiest to get your head around to start with. DC stands for direct current, and this is the kind of electricity that flows in a battery. So if you have a battery in a circuit, has a plus and a minus, the electrons come out of the minus end of the battery and they flow round towards the plus of the battery, because the battery has a potential difference, notionally 1.5 volts, and this pushes the electrons around this circuit, and they flow in one direction at this continuous speed, assuming a constant current, and that's why we call it direct current, because it's current going from A to B at the same rate, doesn't change, assuming that the resistance and so on in the circuit stays the same. Now, alternating current is not like that at all, because what's happening with alternating current is that the plus and minus in the circuit is flipping backwards and forwards at, if you live in the UK, 50 times a second, 50 hertz. So that's like the battery being turned backwards and forwards 50 times a second. And what that means is that the plus becomes the minus and the minus becomes the plus 50 times a second. And so therefore the electrons start flowing in one direction, and then the current reverses, and so they start flowing in the other direction, and so on. And they keep doing this backwards and forwards in the circuit. If you were to plug an AC alternating current source into an oscilloscope, so you could see on a screen what the current looked like and what the voltage looked like, with DC, you'd see a straight line, which was the voltage, and you'd see a straight line for current. For alternating current, you would see for voltage a wiggly line, a sine wave, because the voltage would be going up, then it would be coming down, reversing, and then coming back to where it started again. The current would do the same. And that's used because when you have a changing current like that, you can create a changing magnetic field. That means that you can create a transformer. So alternating current is far more useful to you because you can step it up and step it down, and that helps in transmission of electricity over very long distances. So when you look at the big pylons which are transmitting electricity coming from power stations, the voltage that those pylons are running at is 175,000, 200,000 volts. They then step that down using transformers to lower tiers of voltage, and eventually 240 volts that comes into your house. If they were using DC, they wouldn't be able to do that, and this would make it very much more difficult to step up and step down voltages in order to get the electricity with the fewest losses into your house.
I understand that. Thank you very much.
You're welcome, Robin.
Pleasure.
Thank you. Lots of questions coming in tonight, Chris. Let's go this time to Graham in Newmarket, who says he's got an optical question. I have one of those strobe front lights for my bicycle, and if I'm riding at night and look straight ahead and see two road signs next to each other, for example, speed limit signs, and if I look straight down the centre of the road, I can see the strobing reflection. But if I look at the sign itself, the strobing effect disappears. What is it in the human eye that reacts to this function? Chris?
Can you just clarify for me what he's saying he's seeing again? So he's got a flashing LED light on the front of his bike or his helmet or something.
Yeah, it's on the front lights for his bicycle.
In the distance.
Yeah.
Speed limit signs, let's say.
Yeah.
He says he looks straight at the signs.
When he looks straight ahead and sees two road signs next to each other, like speed limit signs, if I look down the centre of the road, I see the strobing reflection. But if he looks at the sign himself, that strobing effect disappears. So what is it in the human eye that reacts to this function?
I think what's going on is the relative sensitivity of different parts of the eye to light, and also the peripheral parts of the eye. I don't know how fast the bike light is flashing, but different parts of the eye are also more sensitive to movement and light coming on and off than other bits of the eye. The part of the eye that we focus our attention on, so when you're looking at someone having a conversation with them, the face of the person you're talking with is being focused on a part of the eye called the macula, also known as the yellow spot, which is the most sensitive bit of the eye. That's where you can see the best. Now, that gives you the best acuity, but it's not as good at picking up sensitivity or being very sensitive to low levels of light, because the vision in that part of the eye uses cones, little tiny cones, and these cones need quite a lot of light to run them, but they do give you very, very accurate and precise high-resolution vision. Outside of that bit of the retina, where you don't look at so much detail, but you do need to see objects and notice them quickly so that you can react to them and avoid them if it's something falling on you, or dodge a ball that's going to hit you in the head, or whatever. Those bits of the retina are more often, they're less colour selective, and they're more interested in things that change quickly, and they're more light sensitive. So those are usually rod driven, so you have lots of rods in your retina as well as cones. And what's probably happening is when he's cycling down the road and looking directly at the road signs, the most sensitive bit of the eye, the macula, is looking at the sign, and the amount of light coming back from the sign isn't so great as when he's looking straight through the middle and the sign is falling on the edges of the retina, and that's much more sensitive at picking up the subtle differences between the high light levels and the low light levels when the flashes are coming. And I suspect that's why he's seeing the flashes in the side of his eye, but not when he looks straight at them.
Now then, one from the text actually. Hello, Sue, can you ask Dr. Chris what there was before the Big Bang in the universe, and how could it all come from nothing? Somebody else has sent one in actually to the Facebook page to say, I'd love to hear about your Big Bang theory. Does E really equal MC squared? Chris?
Well, it's really hard to know what came before the Big Bang, because if you think about it, the Big Bang was the moment when our universe was created. And since the universe is everything, we can only really surmise from that before the universe was created, nothing existed. Now, that obviously sounds a bit facetious, and it's difficult to actually say, well, how can something exist where nothing existed before? It's very hard for us to appreciate this, though, because the point that people like Stephen Hawking make is that actually we tend to live in a three-dimensional world with a fourth dimension being time, but the universe and what lies beyond the universe may be multiply more dimensional than that, maybe even 11 dimensions. And it's really hard for us to understand what that means, for the simple reason that we've evolved to live in a three-dimensional world with time being our fourth dimension. So it's very hard for us to appreciate what might also be out there and how what else is out there interacts with the here and now that we can see and interact with. So I know that's a rather rubbishy answer, but we just don't know what went before the Big Bang, and it might be that the Big Bang is what's called the white hole of a black hole. And some physicists have suggested that where you have big black holes that are sucking in matter like cosmic hoovers, at the other end of the black hole, to put it bluntly, the arse end of a black hole, there might be a white hole which is spitting out a new Big Bang somewhere, creating a new universe. And some people say there may be multiple universes, the multiverse, and that hovering, I don't know, a few millimetres from your face is another universe with another Sue Marchant show, another Ask the Naked Scientist, heaven forbid. And this could be going on. We don't know. Scientists are trying to detect whether or not there are multiple universes with various experiments, because what we think, or what physics predicts would happen if such a phenomenon existed, is that although we may not be able to see physically this other universe because light may not transmit between it, gravity, they suggest, would. So there ought to be gravitational waves coming from other bodies and things. So various experiments have been conceived that contest this theory, including one called LISA. And LISA is two satellites that measure their distance between them. It uses laser interferometry. So in other words, you're looking at a laser beam bouncing between two satellites. And if a gravity wave comes in and shifts one of the satellites relative to the other, you should be able to pick up this very subtle change in the distance between the two satellites, because the gravity wave would squeeze the two together a little bit, and this would be demonstrable, and this would prove that there were gravity waves coming in from places. At the moment it's all speculative and we have no evidence for any of it, but people have to start somewhere.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.